For the shear flow in an open section worked example, we're given the information that we're going to use a beam section, so basically an I section, and we want to calculate the shear flow distribution at the midpoint. So that's just midway along whatever length of beam we're going to look at. If the section is used as a 5 metre long cantilever with a 10 kilonewton point load acting downwards, so in the negative x2 direction at the free end, we're given some other information in terms of the material properties that we can assume, and then we're going to use I11, so the second moment of area, based on centerline simplifications or area simplifications, and the reason we're doing that is simply for consistency. So because when we go through the calculation for shear flow, we're effectively going to be using the centerline, it makes sense to use a simplification rather than use the value that we would get from the section table. The second part of the question is we're required just to check that the integration of the shear stress returns the shear force. So this is basically going to be done by integrating the shear flow. So remembering that the shear flow is equal to the shear stress, which we're assuming is constant across the wall thickness, multiplied obviously by the thickness. And so we're going to be looking particularly in the web section, because it's in the web section that the shear flow is in the same direction as the shear force that we've got in this particular case. Part 3 is just to state whether the shear stress distribution will vary at other locations along the length of the cantilever. Now this is really to make sure that we appreciate that the shear flow distribution, and hence the shear stresses, will vary depending on whether we have different values of shear force from one location in the beam to another. And then the final part is just to state whether the beam will yield under shear. So generally the reason that we're checking for shear is obviously to see whether it presents an additional way in which the material, so the steel that the beam's made of, might actually fail. And so it's just something that we should do. You can also find that shear increases the deflection, but that's a little bit beyond the scope what we're going to look at here. The first thing I've done is just draw out all of the information that we have. So I've obviously looked up the section in the section tables, and I've just checked the dimensions from those. So these are the dimensions as I've set them out, obviously just including a little bit of extra information in terms of things that are going to be useful for us when we're calculating I11, for example. I've then drawn out the actual loading scenario we have. So the cantilever obviously is 5 meters long. We have the fixed end here, and then the 10 kilonewton point load acting down the way in the x2 direction at the free end here. And what I'm doing in order to calculate the shear force at any point along here is I'm just imagining I'm taking a cut, and the convention I'm using is that the shear force V2 will be positive if it's going in the positive x2 direction. So looking at the loading setup that we have, obviously we would have a reaction force at the fixed end here of 10 kilonewtons going up the way. And so if we look at equilibrium at the cut, then that means that we must have a shear force of 10 kilonewtons coming down the way. And so that's why on the shear force diagram, we're taking as a negative shear force. We'll come back really to the significance of the sign just later on when we integrate the shear flow or integrate the shear stress in order to check that we do return the shear force appropriately. And I'm just noting here, because we only have a shear force in one direction, we can use this version of the shear flow relationship. So obviously little q is the shear flow, and it's dependent on the distance that we've gone within the cross section along the center lines. And obviously we just have shear force here, the first moment of area, which is also dependent on the distance we've gone along in center lines, and then divided by the second moment of area here. In terms of how we're going to progress around the section, we're going to go from points where we know that the shear stress must be equal to 0. So for example, here and here, we know that the shear stress will be equal to 0, and the reason for that is because there's no material beyond that point, there's nothing for the material within the cross section to shear against, and hence we have a shear stress of 0. Calculating the second moment of area, obviously we know how to do this for an I section by now, it's very familiar to us. So we just have this term here, obviously is for the area of the web here. This term here is for the two flanges, the local contribution to I11. And then finally this term here is the area times x2 bar squared for the flanges, so top and bottom. And the reason obviously that the web doesn't feature in this is because the centre of the area of the web is the same as the centroid for the cross section overall. And we just end up with a value approximately 3% less than the value in the section tables, and that's to be expected because we're obviously missing out the radial parts here that there would be in a hot rolled I section. Coming on to how we're actually going to calculate the shear flow. So we're going to progress around the section, first of all from 1 to 3, then from 2 to 3, and whatever result we get going from 1 to 3 and 2 to 3, we'll add those together because the flow into a joint must equal the flow coming out of a joint. And then we're going to progress from 3 to 4. So the reason we're doing that is we should instinctively recognise that the shear flow or the shear stress is going to be maximum at the neutral axis, which for an I section will obviously be at the mid-height of the web. And then finally we're going to progress from 4 down to 5, and then from 5 to 6 and 5 to 7. Now, because the thickness of the flange is equal going in this direction and this direction, we'll assume that the flow, a little bit similar to how we would have in a pipe network, as it comes down here, it's going to split equally off in this direction and in this direction. We're going through the calculations in a little bit more detail than we normally would. So as you practice these things, you'll get used to knowing which parts we expect to have a linear variation and which parts we expect to have a parabolic variation of shear flow in. So within the flange, either going from 1 to 3 or 2 to 3, so from 1 to 3 as we're doing in this case, the first moment of area will just be equal to the thickness multiplied by the distance that we've gone, so S subscript 1 here, and then multiplied obviously by a constant x2 bar value. So that means that we're just going to have a linear variation of the first moment of area, and that in turn means we'll have a linear variation of the shear flow, and it's just dependent on this distance S1 here. So setting up the shear flow calculation, we obviously have the value of V2 here, the value of Q1 as a function of S here, and then just divided through by the value of I11. Going from 1 to 3, I'm obviously just going half the total width of the cross section, so that's why I've marked in S1 equals to this value here. Just substituting in then the values, so we end up with this value of shear flow going from 1 to 3. Just noting that if we were going from 2 to 3, we would have essentially exactly the same calculation, so we'll come up with the same value. And if we want to add them together, so all I'm doing here is I'm saying that we've gone S1 and S2, both of which would be half of the total width of the cross section. So we just have the total width of the cross section in here, and we find what we expect to, which is at this value here, so the value just at the top of the web before we start going down the web is equal to double this value. So it's simply the values added up, going from 1 to 3 and then going from 2 to 3. Going from 3 to 4, so I'm going to do the total calculation for the first moment of area. So I have here the thickness and then obviously multiplied by S1 plus S2. So these will be the total width of the cross section, multiplied by the x2 bar value, which is obviously constant to the flange, and then plus, so the thickness of the web. As we progress down the web, obviously the area increases as we go down S3, but the distance to the centre of that area will be the distance to the flange, and then just minus the distance that we're progressing down, obviously divided by 2. And because we have an S3 term here and an S3 term here, this is what tells us that we're going to have a quadratic distribution of the shear flow within the web part of the cross section. So just doing the calculations, obviously this is the value we were expecting at the top of the web, and then we have this is essentially the changing term as we go down the web, and we then just have this value once we reach 4 for the value of Q1. Putting all of that information in, so this is now the total distance that we've progressed. So effectively this is S1 plus S2 plus S3 going down to the centroid of the cross section, and so we end up just with this value of the shear flow at that location. We can continue down the web with the same equation. So what I've got here is the constant shear flow value effectively. So this was the web contribution, or rather the constant first moment of area contribution from the web. And then as we go down, although I've said we're going from 4 to 5, I've actually taken it as if we're going all the way from 3 to 5. But the important thing to note is that this term here now simply comes to 0. So the implication of that is that by the time we get to the bottom of the web, we have the same value for the first moment of area as we did at the top of the web. And so that means that we're going to have the same value of shear flow at the bottom of the web as we did at the top of the web. Just confirming the calculation, so as we expected, we have the same value of shear flow at the bottom of the web as we had at the top of the web, and we have a parabolic distribution going down from the top to the bottom. The final thing, and we wouldn't normally need to do this because we'd be able to take advantage of mirror symmetry, but just obviously to state that when we get to 5, the shear flow is going to divide evenly because it's the equivalent of having the same thickness or the same diameter of pipe, just to use a sort of conceptually similar idea of flow. So going from 5 to 6, we just want to check that we do go back to 0. So I've just first of all split the first moment of area, which is essentially very similar to splitting the shear flow. And obviously we have now minus, so minus because the x2 bar value is actually negative. So the thickness times S4, and by the time S4 has reached the value of half of the total width, we find that we end up here with a first moment of area value of 0, and hence we would have a shear flow value of 0. So this is really just confirming what we expect, because obviously when we get to the two ends of the flange at the bottom, we have the same situation as we had at the two ends of the flange at the top. That is to say that we don't have any material to shear against, and hence the shear flow and the shear stress must be equal to 0. So I've just obviously noted here that the total centerline distance that we've progressed through is this value, and it will be equal to 0 at that value. The final step before we complete the shear flow diagram, and again we wouldn't normally do this, this is really just fully satisfying ourselves. Normally we would exploit mirror symmetry, so it's just confirming that if we do the same thing going from 5 to 7, so basically the same calculation as we had before. Again, this is a negative because we have a negative x2 bar value in this situation. So by the time we've gone through the entire centre line of the cross section, so all of the distances in the flange and the web and then the bottom flange as well, we do end up back at a value of shear flow just equal to 0. So drawing all of that information out, this is the diagram that we end up with. It's only when we come to drawing the diagram that we actually begin to be concerned by whether we had positive or negative values of shear flow. And we're also, if we just have a shear force V2, that means that we're particularly interested, so the thing that's going to decide in terms of the direction in the other parts of the cross section is the direction of shear flow that we have within the web of the section. Now, because we had a negative value here, what I've gone on to do, and this is my preferred way of doing things, so I've included essentially all positive values of shear flow on the diagram, but then the direction of the arrow indicates the actual direction of the shear flow, and it's because we had a negative shear flow when we were in the web that this arrow here, so the arrow indicating the direction in the web, is down the way, so it's in the negative x2 direction. Because we're using this concept of shear flow, although it doesn't actually represent the flow of material, we're using the concept that it is similar to the idea of flow. And so once we've clarified the direction that we have in the web, the direction that we have for the shear flow in the flanges, this is really the only thing that makes sense in terms of the concept of flow. So we couldn't suddenly, for example, have flow coming down the way in the web but going out the way in the top flange, and similarly when we have the flow coming down the way in the web, we wouldn't then expect flow to suddenly go in the flange back towards that point. So the general rule to remember is to check the direction relevant to the shear force that you're applying, and we're expecting that the web is doing the majority of resisting that shear force, or if we integrate the shear stresses in the web, we should return the shear force, and just then be consistent with how the shear flow must be going around the cross section. So this is really the main point of this diagram, is that the arrows indicate the directions of shear flow. To try and make really clear what's going on, I've just imagined that I've taken a little cube of material out from the web. So in the case of the web, it could be from anywhere from the top to the bottom. And what I've done is I've just drawn the axis system here. So obviously when we look at the cross section, so we're plotting the distribution of the shear flow in the cross section. The cross section exists in the x1, x2 plane, and then the x3 direction is obviously the direction running along the length of the beam. And I just wanted to highlight that the direction of the shear flow in the web in this case is going down the way, so in the negative x2 direction like so. But because of the principle of complementary shear, that does mean that there'll also be a shear flow going back in this direction here, so back along the length of the beam. Similarly for the flange, so I've imagined that I'm taking part from the top up here, so a little cube out of the flange. So the shear flow on the front face here, this is actually the direction that we have based on this diagram, so based on the direction of that arrow. But it's again to note that that means through the principle of complementary shear stress, we actually have a shear flow going back along the direction of the beam here as well. When we come on to checking that if we integrate the shear flow or if we integrate the shear stress values, we end up returning the shear force. The reason that we're only going to go through and integrate the shear stress or the shear flow in the web is because you can see this is the only one that's in the direction, the same direction as we have for V2. So this is the only one that's going in the x2 direction like so. The reason we don't include anything from the flange is obviously neither of these, so the one on the front face or the one on the side face, is in the x2 direction, and so in terms of integrating them, we wouldn't expect them to return anything useful when we're checking that we get V2 returned. Straight away what I've done is, rather than actually integrating the shear stress, so we do know that we expect the shear stress to be constant across the thickness. So the shear flow, which is what we've actually calculated, is just equal to the shear stress multiplied by the thickness. And so therefore, in order to return V2, we should just integrate along the length of the web, and we're just integrating obviously the values of the shear flow along there. So we're going to numerically integrate. So what that means is I'm going to take a constant part. So this was the shear flow at the top and the bottom. So effectively that gives us a rectangular part, or a rectangular area if we multiply it by the total length of the web. And then for the parabolic part, I know essentially for numerical integration that if I take 2/3 of the area of the equivalent rectangle, that will return the contribution of the parabolic part. So this was obviously the maximum shear flow, and then just minus the shear flow at the top and the bottom, and multiplied by the total length of the web. So adding those two together, we do end up with a value that's just a little bit larger than the value of V2 that we had. However, because we know that there are going to be some geometric errors, particularly because we used simplifications to calculate I11, for example, I'm going to accept this value as it's really a very low percentage out from the 10 kilonewton value that we were expecting. I could obviously have put the negative sign in because the shear stress is going in the negative x2 direction, and in that case I would have actually returned negative 10 kilonewtons, which is obviously what we're really expecting. So the final two parts of the question, so part 3 is very straightforward. So because the shear force is constant along the cantilever, we can assume that we have the same shear flow distribution and hence the same shear stress distribution. In terms of tau max, so the maximum shear stress, we need to check both in the web and the flange. So because the thickness of the web is smaller, and because we have obviously Q is equal to tau T, so wherever the thickness is lower, that means the shear stress must be higher. So I'm finding tau max in the web, so we just have the maximum shear flow value in the web divided by the thickness. And because we find this is really quite low, so 5.5 or 5.6 newtons per millimeter squared, it's much lower than we would have if we were looking at the material failure due to shear stress alone. If I wanted to be a bit more rigorous about this, what I should calculate is I should calculate the normal stress value due to bending as well, and then I should calculate something like the von Mises stress value, so the von Mises stress distribution throughout the cross section. I haven't gone on to do that because we're simply interested in the shear contribution in isolation at this stage. Final thing, just to make sure people are clear on, so when we're dealing with shear stress due to shear force, the assumption is that we generate shear flow, and the requirement for that is that we're assuming that the shear stress at any particular location is constant across the thickness. So this is why obviously the shear flow value is just given by the shear stress multiplied by the thickness.